Hello friends, welcome to True Event Academy. In the last lecture we were discussing the moment of inertia of various rigid bodies. So in the last lecture we have discussed up to circular disc. So in this particular lecture we will discuss solid sphere onwards in this particular lecture. So what we will discuss in this lecture is moment of inertia of solid sphere, hollow sphere, ellipsoid and right circular cylinder. So let's start our discussion with the moment of inertia of solid sphere. Okay, so how a solid sphere is generated. Okay, so when a semicircular area, let us take a semicircular area. So this is our semicircular area. So when a semicircular area is rotated about 360 degree, then a solid sphere is generated. So let us rotate this with 360 degree. 360 degree. So we have a solid sphere. On rotating this about 360 degree, we have a solid sphere. Solid sphere of radius A. So for finding the moment of inertia, let us take an elemental area at an angle of theta to the horizontal. Okay, so the elemental change in theta will be d theta. So let us take an elemental area. Okay, and this is r at a distance of r. So the elemental change in r will be dr, and this distance will be r d theta. Okay, so what will be dr? Sorry, what will be the elemental area? That is dA. So this is our elemental area. Okay. So the elemental area is dA. dA is equal to, this is dA. So we have dA is equal to dr into r d theta. Okay. So on rotating this dA about 360 degree, we get a ring, elemental ring. So let us draw a ring. So ring will be of cross section dA and the radius will be r sin theta. This distance is r sin theta. Because in this triangle we have this distance as r and this angle is theta. So this is equal to r sin theta. Okay, so the radius of the elemental ring will be r sin theta and cross section is dA. So let us draw an elemental ring. So we have the elemental ring like this. Okay, and this ring will have a cross section area of dA. Okay, so this is the cross section area dA, and the radius will be r sin theta. This radius is r sin theta. Okay, so this is our radius. So we have studied that in an elemental ring. So we have studied in the moment of inertia of the ring. The moment of inertia of ring is mr square. Okay, so here the mass is, so mass of this elemental ring will be dm. This is of dm and radius is r sin theta. So what will be the moment of inertia of the elemental ring? So we have the elemental moment of inertia of elemental ring will be dm into radius is r sin theta, dm into r square, that is r sin theta whole square. This is the moment of inertia of this elemental ring. Okay, so let us find the elemental mass. Okay, so when we rotate this dA about the whole about 360 degree, it will cover the whole perimeter. So the perimeter will be 2 pi into r sin theta. So area into perimeter will be the volume of this ring. So let us find the volume dV. dV is equal to area into perimeter of the elemental ring. So perimeter of elemental ring. So this is equal to dA is dr into r sin theta is the area. Sorry, dA will be dr into r d theta. dr into r d theta into perimeter will be 2 pi into, let us take this as y, radius is y, the 2 pi into y, and let us place y as r sin theta. So 2 pi into r sin theta. Okay, so this is our elemental volume. So what will be the elemental mass? So elemental mass will be rho dV. This is rho times of, this is rho into, this is 2 pi into r is here and r is here, 2 pi into r square dr into sin theta d theta. Okay, So now the elemental moment of inertia of this elemental ring will be di is equal to dm into r sin theta whole square. So let us write this. So we have the moment of inertia of elemental ring will be rho dv, that is 2 pi rho r square dr into sin theta d theta. Okay, so let us integrate this. So integration for getting the moment of inertia of the complete solid sphere. So the moment of inertia of the solid sphere I will be integration of dy, that is integration of that elemental ring. So the elemental ring, the theta will be varies from 0 to pi, because on varying the theta from 0 to pi, this elemental ring will gets covered in the whole area. Okay, and it will generate the whole volume, because on varying this theta, this ring will cover the whole cross section. Okay, the whole area will gets covered. Okay, so this elemental ring will cover the whole region. Okay, in particular we can call this as region. Okay, so if theta is varied from 0 to pi, this ring gets covered in the whole region. Ultimately the complete solid sphere is generated. Okay, so the limit from theta will be 0 to pi. This is 0 to pi, and r is from, because this radius is of a, radius is a, so r varies from 0 to a. Let us integrate this. So this is r square dr. This is dv is dr into r d theta, and this is dm into r square. Actually, moment of inertia will be dm into r square. Actually, this is dm actually. So we have the moment of inertia is dm into r sin theta whole square. So we have the moment of inertia as di is equal to dm into r sin theta whole square. So let us place the value of dm. So we have this as dm is rho into 2 pi r square sin theta, r square sin theta dr into d theta into this is r square sin square theta. Okay, so this is equal to 2 pi into rho, and this is r4 into sin cube theta dr into d theta, and we have the integration. The integration is from r is from 0 to a, and theta is from 0 to pi. This is the value of on integrating this elemental ring, we get a moment of inertia of the complete solid sphere. So we have this as I. So this is equal to, and this is r4 into dr. So integration will be r5 upon r5 upon 5, and after putting the limit as a, so we have this as 2 pi into a. Let's take it at common. So we have r4 into dr. Integration is from 0 to a. Okay, into this is sin cube theta into d theta, and the integration is from 0 to pi. Okay, so we have this as I is equal to 2 pi into rho, and this is r5 upon 5. So after putting the limit, we have a5 upon 5, and this is sin cube theta d theta, and the limit is from 0 to pi. Okay, so let us divide this by 2 and multiply by 2. So 2 we can take it here. This is 2. So this is equal to 4 pi rho into a5 upon 5, and this is this, how we can integrate this we have studied in calculus, sin cube theta d theta. This we can write as n upon n minus 1. So this is 3, and 3 minus 1 is 2. So this is 2 by 3 into 2 by 3. So this is equal to 8 pi rho a5 upon, this is 8 pi rho a5 upon 15, and we have the density as, since the mass is concentrated throughout the volume, so we have rho is equal to mass upon volume. So volume is 4 by 3 pi a cube. So this is equal to 3m upon 4 pi a cube. Okay, so let us place the value of rho. So this is equal to 8 pi a5 upon 15 into rho की value 3m upon 4 pi a cube. Okay, so this gets cancelled with 3 5 is 15 and this is gets cancelled. This is 2 by 5 ma square. Okay, so we have the moment of inertia as moment of inertia of solid sphere of mass m and radius a as this is 2 by 5 ma square. Okay, so we have discussed up to solid sphere. Okay, so now let us discuss hollow sphere. So let us discuss the moment of inertia of hollow sphere. Moment of inertia of mass m and radius is a. So how a hollow sphere is generated? So if a semicircular arc is rotated about 360 degree, then a hollow sphere is generated. In the earlier case of solid sphere, we have rotated the semicircular area, but in this in case of a hollow sphere, we have to rotate the semicircular arc. So let us rotate the semicircular arc. So how a hollow sphere is generated? When a semicircular arc. So let us rotate it semicircular arc. This is our semicircular arc of radius a. So this is our radius a. Okay, so when a semicircular arc of radius a. So let us take an elemental arc at an angle of theta. So at an angle of theta, let us take an elemental arc. At an angle of theta, let us take an elemental arc. And the elemental change in the theta is d theta. This is d theta. So what will be the arc length, elemental arc length? So this is this is will be, because the radius is a, this is a d theta. Okay, so on rotating this complete arc about 360 degree, a hollow sphere is generated. So on rotating this about 360 degree, we get a hollow sphere of radius a. Okay, so on rotating this elemental arc, on rotating this semicircular arc, this elemental arc will also get rotated. So this is our elemental arc. This will also get rotated. Okay, so an ring ring will be generated, and this area is of. So what will be the area? What will be the surface area of this elemental ring? The surface area will be arc length into the perimeter. So this arc length is, this elemental arc is a d theta. This is a d theta. This red mark portion length is a d theta. A d theta. So a d theta into perimeter. So this radius will be a sin theta. This is a sin theta. So this radius is a sin theta. So and the perimeter will be 2 pi into a sin theta. So what will be the complete area? So complete cross section area is equal to this is arc length a d theta into perimeter. So perimeter is 2 pi into a sin theta. Okay, so this arc is rotated about 360 degree. Then this cross section area of the ring will be surface area of the ring will be a d theta into, this is perimeter. So this is our perimeter, and this is elemental arc length. Okay, so this is the surface area. Surface area. This is not the cross section area. This is the surface area. Okay, so this will be equal to 2 pi 2 pi times of a square 2 pi a square sine theta into d theta. This is the surface area. On multiplying the surface area with the density, we get the mass, because in case of this, the density is mass upon surface area. So the surface area is 4 pi a square, and this case of this elemental ring, the surface area is surface area is equal to this one. Surface area times surface area is given by this expression. Okay, this is our surface area. So elemental mass will be elemental mass dm is equal to density times surface area. So this is equal to rho times of 2 pi a square sine theta into d theta. 2 pi a square sine theta into d theta. This is the elemental mass of this ring. So what will be the moment of inertia of the elemental ring? The moment of inertia will be di is equal to dm into radius square. This is a sine theta whole square. So we have the moment of inertia of the elemental ring di is equal to elemental mass into radius square, that is a sine theta whole square. So this is equal to dm is 2 pi rho a square sine theta d theta into a square sine square theta, a square sine square theta. So we have this as 2 pi rho into a4, 2 pi rho into a4. This is sine cube theta into d theta. So let us integrate. So the theta will be integrated from 0 to pi. If theta is varied from 0 to pi, this ring will cover the whole region. Okay, so whole surface area will get covered when we vary this theta from 0 to pi. So this is varied from 0 to pi. So this is equal to 2 pi rho a4 into sine cube theta d theta. This is integrated from 0 to pi. So this is equal to 2 pi rho a4 into, this is divide this by 2 and multiply by 2. 2 we can take out. This is 2 times. This is 4. 4 pi rho a4 into 2 upon 3. This we can solve as sine cube theta d theta. Integration is 0 to pi by 2 is 2 upon 3. This is 8 pi rho a4 upon 3. This is our, and on integrating this, we get the moment of inertia of complete surface area of the hollow sphere. This is I. So I is equal to 8 pi a4 upon 3 into rho, and value of rho is m upon 4 pi a square. This is m upon 4 pi a square. So this gets cancelled by 2a square. So this is equal to 2 by 3 ma square. So 2 by 3 ma square is the moment of inertia of hollow sphere. This is 2 by 3 ma square. Okay, so what we have done? So we have rotated the this arc. Okay, so this elemental arc is rotated about 360 degree. Then it has generated an elemental ring. Okay, so for the elemental ring, we have the moment of inertia as dm into, dm is the elemental mass of this ring, and dm into radius square is the moment of inertia of the ring. So dm into a sine theta square. And how we have calculated the dm? Since it's state of a hollow sphere, the mass is concentrated throughout its area. So the mass will be density times elemental area. So we have this as surface area is this arc length into whole perimeter. So then we have calculated the surface area of this elemental ring. So we have the surface area of elemental ring as elemental arc length into perimeter. So this we have found the surface area. On multiplying the surface area with the density, we have calculated the elemental mass, and from here we have calculated the moment of inertia of this elemental ring. So on integrating this from 0 to pi, we get the moment of inertia of this complete surface area of the, that is of the hollow sphere. Okay, So this we are getting this as 2 by 3 ma square. Okay. So now let us discuss about the ellipsoid. So we have discussed up to the hollow sphere. Okay, so now let us discuss about the ellipsoid. Okay, ellipsoid and the right circular cylinder we have to discuss. Let us find the moment of inertia of ellipsoid. Moment of inertia of ellipsoid. Moment of inertia of ellipsoid, semi-axis as ABC. Okay. So how we can find this? So let us draw a ellipsoid that is lying in the first quadrant, that is above the xy plane. So let us draw an ellipsoid. So this is our axis. Let us take this as x and this as y. So let us draw the ellipsoid. Okay, so basically there are 8 quadrants. So 4 are above the xy plane and 4 are lying the below the xy plane. Okay, so we will find the moment of inertia of one of the 8 portions. Okay, so total there are 8 portions that is constituting the whole ellipsoid. So we are finding the ellipsoid in the 1 upon 8th region. Okay, so we are calculating this in the first quadrant, and after that we will multiply this with 8 for getting the moment of inertia of this whole ellipsoid. Okay, so let us take an elemental mass here. Okay, so let us take an elemental mass. Okay, so the volume, this is volume, will be dv will be elemental change in the distances, that is dx into dy into dz. Okay, so let us take this uh, this is x, this is y, and this is z. So we have this change in, so this distance will be, because this is y axis, so this distance will be y and this distance will be z. Okay, so what will be the distance from the x axis? Distance of this elemental mass from the x axis. So this distance will be y square plus z square under root. Okay, let us take this as r. Okay, and what will be the elemental mass? So we have the elemental mass dm as rho times of dv, rho times of dx, dy and dz. Okay, so we have the moment of inertia. Moment of inertia of this elemental mass is equal to, this is r, so this distance is r, so we have r square into dm. Okay, this is integration. So we have this as moment of inertia that is lying in the first quadrant. Okay, so moment of inertia in the first quadrant. Okay, so this is equal to I1 is equal to r square into dm, and we have r square as y square plus z square into dm. This is rho times of dx, dy and dz. Okay, so now we have we will apply the Dirichlet's test. Okay, for solving this. So we have the equation of the ellipsoid as x square upon y square, sorry, x square upon a square, and the semi axes are, this is of length a, this is of length b, and this is of length c. Okay, so this length is a, this OX, this is O and this is X. So OX is a, this is OY is B, and OZ is C. So we have x square upon a square plus y square upon b square plus square upon c square is equal to 1. So let us take x square upon a square as u, y square upon b square as v, and z square upon c square as uv, and this is w. So from here we have x is equal to a into u 1 by 2, and we have y is equal to b v 1 by 2, and from here we have w is equal to c z 1 by 2. Okay, so the change in value of, sorry, this is from here we have z is equal to c into w 1 by 2. So from here we have dx is equal to a by 2 into u minus 1 by 2 du, and we have dy as dy is equal to b by 2 v minus 1 by 2 into dv, and from here dz is equal to c by 2 w minus 1 by 2 into dw. So what will be the value of dx dy dz? Dx dy dz is equal to, this is a by 2 b by 2 c by 2, so this is a b c upon 8 into, this is u minus 1 by 2 v minus 1 by 2 w minus 1 by 2 into du dv and dw. Okay, so this is the value of dx dy dz, and this is the value of dx dy dz. So let us place here. So we have this I1 is equal to y square plus z square. Let us place the value of this um, y square and z square first. So y square is, value of y is this, so this is b square. Let us take rho here, rho times of b square, b square into v plus z square, this is c square into w. Okay, into dx dy dz, this is abc upon 8 u minus 1 by 2 v minus 1 by 2 w minus 1 by 2, and this is du dv and dw. Okay, so let us further simplify this. This is u minus 1 by 2 v minus 1 by 2 w minus 1 by 2, and this we have y square as, y is b v 1 by 2, so this is b square into v, and this is c square into w. So let us further simplify this. So we have I1 as, so I1 is equal to rho into ABC upon 8 into, and this we have b square into u minus 1 by 2, and v is 1, and this is minus 1 by 2, this is v 1 by 2, and this is w minus 1 by 2. Okay, plus c square into u minus 1 by 2, v minus 1 by 2, and w 1 by 2. Okay, into du dv and into, we have this as du dv and dw, this is du dv and dw. Okay, so we have this as I1 is equal to rho ABC upon 8, and this is, this we can write as b square into u 1 by 2 minus 1, this we can write as 3 by 2 minus 1, and w we can write as 1 by 2 minus 1. Okay, plus c square u 1 by 2 minus 1 v 1 by 2 minus 1, and this is w 3 by 2 minus 1, and this is du dv and dw. Okay, so this we can write as I1 is equal to rho ABC upon 8, and this we can write as b square into gamma 1 by 2, gamma 3 by 2, and this is gamma 1 by 2. We are using the Dirichlet theorem. Okay, so upon addition of all these plus 1, so this is 1 by 2 plus 3 by 2 plus 1 by 2 plus 1 plus c square. c square into 1 by 2. This is 1 by 2 and this is 3 by 2 upon 1 by 2 plus 1 by 2 plus 3 by 2 plus 1. This is gamma. This is not root, this is gamma into du, dv and dw. Sorry, this is not there. Okay, so let us solve this. We have the value of I1, that is moment of inertia that is lying in first quadrant. I1 is equal to rho ABC upon 8 into B square. This is actually 7 by 2. Let us write this as 7 by 2. 7 by 2 gamma. This is 7 by 2 gamma. Okay, so we have n plus 1 gamma is equal to n gamma n. So we have 5 by 2 plus 1 is equal to 5 by 2 gamma 5 by 2. 5 by 2 we can write 3 by 2 plus 1. This is 5 by 2 into 3 by 2 gamma 3 by 2. So this we can write as 15 upon 4. This is 15 upon 4 gamma 3 by 2. This is same as 15 upon 4 gamma 3 by 2. Okay. So this gets cancelled, 3 by 2, 3 by 2. And this is 3 by 2, 3 by 2. And we have gamma 1 by 2 is root pi. So this is gamma 1 by 2, gamma 1 by 2 whole square, and this whole value will be pi. Okay, so this will be b square into this is pi upon this is 15 upon 4. So this is into 4 upon 15. Okay, similarly we have this as plus c square into this is 4 pi upon 15. So this we are having this rho ABC upon 8 into 4 pi upon 15 b square plus c square. This is I1. Let us place the value of rho. So we have the density. So the volume of this ellipsoid will be um, 4 by 3 pi ABC. So we have rho as mass upon volume 4 by 3 pi ABC. So this we are having 3m upon 4 pi ABC. Okay, so we have 4 pi ABC rho. 4 pi ABC rho. This is equal to 3m. So 4 pi ABC rho. This is 3m upon 8 upon 15 b square plus c square. This is moment of inertia I1. So the moment of inertia of complete ellipsoid will be 8 times, because this is 1/8 portion. So we have the moment of inertia because 4 are lying above the xy plane and 4 are lying below the xy plane, and we have calculated for only one single portion. So we have this, the moment of inertia of complete ellipsoid is 8 I1. So this is 8 of 3m upon 8 into 15 b square plus c square. So this gets cancelled and 3 gets cancelled with 5. So this is m by 5 b square plus c square. So this is the moment of inertia about OX. So we have to find the moment of inertia about. So moment of inertia about OX will be m by 5 b square plus c square, because we have taken this distance from OX, the axis that is x-axis. So we have taken the distance of this elemental mass from the x-axis, because we have taken this particular length, that is y square plus z square. We have taken the distance from y and distance from z. Ultimately this value will be y square plus z square under root, that is r. So for getting the moment of inertia about OY, that is y axis, so this will be m upon 5 a square plus c square. Okay, and OZ will be, that is about z axis, m by 5. This is a square plus b square. So this is our moment of inertia of the ellipsoid, mi of ellipsoid. about OX, OY, OZ. Okay, so we have discussed up to ellipsoid. So now we will discuss the right circular cylinder. So now we have discussed up to ellipsoid. Now we will discuss moment of inertia of right circular cylinder of height h and radius a. So let us discuss this. So moment of inertia of right circular cylinder of radius a and height h. So let us find this. So let us draw a right circular cylinder. So we have the right circular cylinder like this. Okay, so let us take an elemental plate and this height is h. Okay, so let us take an elemental plate of thickness dx at a height x. Okay, from this bottom, and we have the radius as a. Okay, so this is our elemental plate. So we have the so this thickness is dx, and we have the area as pi a square. Okay, so the volume, elemental volume of this volume of this plate, volume of the plate dV is equal to area. So area is pi a square into dx. Okay, so what will be the mass of this elemental plate? So we have dm is equal to rho times of dV. So this is equal to rho times of pi a square into dx. This is our elemental mass. So what we have studied, the moment of inertia of a plate of mass dm and radius as a. So the moment of inertia is di is equal to the moment of inertia for the plate is mr square upon 2. So this is dm into r square, a square upon 2. So the moment of inertia di is equal to a square by 2 into dm. So dm is rho pi a square into dx. Okay, so what will be the moment of inertia of the whole cylinder? Okay, so the integration of x will be from 0 to h. So let us integrate this. So we have 0 to h, and on integrating this elemental plate we get the moment of inertia of complete cylinder. So I is equal to rho a4 pi upon 2 into h, and we have the density as, so volume of the sphere will be pi a square into h. So let us place the value of rho, this is mass upon volume, so volume is pi a square h. Let us place the value of rho here, so into mass upon pi a square h. So this gets cancelled and pi gets cancelled. This is ma square upon 2. Okay, so the moment of inertia will be ma square upon 2. So this is moment of inertia ma square upon 2. Okay, so we have discussed up to right circular cylinder. Okay, so in the complete series of moment of inertia of various rigid bodies, so we have discussed about the moment of inertia of rod, moment of inertia of rectangular lamina, moment of inertia of rectangular parallelepiped, triangular lamina, elliptical disc, hoop or circumference of a circle, circular disc, solid sphere, hollow sphere, ellipsoid, and right circular cylinder. Okay, so this is all about the moment of inertia of various rigid bodies. Thank you.